Our next speaker, Dr. Brian Diefenderfer, is an Associate Principal Research Scientist at the Virginia Transportation Research Council in Charlottesville, where he has worked for the past 15 years. His research focuses on providing better tools for VDOT to use when designing and rehabilitating its pavement network, including pavement recycling techniques. Brian received his bachelor's, master's, and doctoral degrees in civil engineering from Virginia Tech, go Hokies, and is a licensed professional engineer in the Commonwealth of Virginia. With that, hand it over to Brian.
Thanks very much, Eric, and thank you to the folks at ERA for the invitation to come here to talk, and thanks for everybody for sticking around to the bitter end. So I was asked to talk about the work we're doing on the NCHRP 962 project. This is a thing we've had ongoing for about the past 2 years. Dave Jones, who came and talked yesterday, is the co-PI on the project. I'm serving as the PI, luckily to serve as the PI on the project. It's a great group of folks. And so I'm going to talk a little bit about the progress we've made in the study so far and where we're heading with it. So the objectives of the study, and this really kind of hit home maybe more to me, I guess, the day before yesterday at the Cold Recycling Committee meeting, talking about testing for acceptance by agencies and testing for, I guess, quality demonstration by the contractors, and how long that process takes. So the objectives of our study were really to try to come up with processes or methods to be able to do that work much faster. And so formally, the objectives that were laid out for us were to develop time-critical tests for asphalt-stabilized FDR, CIR, and CCPR. So we're running the gamut of the asphalt-stabilized recycle world. And then develop guide specifications on how to use these materials for agencies to give them a basis for when the materials and layers can be open to traffic and then also surfaced. So we've really got in some ways a narrow focus, but really looking at short-term quality tests for the recycled materials. In terms of the project team, as I said, I'm leading the project. Dave Jones is the co-PI. Adam Hand from University of Nevada, Reno is working on the project, as well as Ben Bowers, who used to be in my office, is now at Auburn University. Gerardo Flinch is at Virginia Tech, and Ilker Boz and Johnny Habush are with me at VTRC. So this is the team we have working on the project. It's a large team, but it's a large project too. So all these folks have been really instrumental in performing the work. So the work accomplished so far, it was a 3-year study when we were awarded the contract the other year. The first year was the phase 1, the literature review and a stakeholder survey. And I know a lot of people in this room contributed to the stakeholder survey, online survey, so I appreciate your input on that. We reviewed agency specifications and started to identify the preliminary tests that we wanted to work on. That work was completed. That was the first year. Last year we worked, and up to maybe the beginning of the summer, we worked on phase 2, and that was all based on laboratory testing. And again, a lot of folks here provided materials for us to test. I asked contractors to send me materials, about a dozen 5-gallon buckets of the wrap or whatever the source material was, plus any of the recycling agent or stabilizing agent to be able to process that material, and mixed design data and all kinds of stuff. And so many folks in here were very helpful and sent me all that material, all that data without question. And so I really appreciate the help on that. So that work was completed earlier this summer, and then late this summer and this fall we started going on phase 3, which is taking these tests out to the field. So we visited 6 locations around the country so far, and we'll probably do, I think Dave has got 1 or 2 more here coming up in California, and then we'll probably do a little bit more work in the spring. So in terms of the spec review, if you look at the map, the agencies, or excuse me, the states and provinces shaded in blue are where we found specifications for asphalt stabilized, again, FDR, CIR, CCPR, either a state agency or provincial agency or a municipal agency. And we review those specifications. And actually, we turned that into a TRB paper that will be presented at TRB here in January. So look out for that. In terms of specifications of the things we found, diversity in general is good, but not when you're talking specifications. We found a lot of variation in the specifications, so my heart goes out to the contractors that are working across multiple states and dealing with some of those things. The design acceptance tests we found vary widely. As an example, curing times in some places are based on moisture content, some places they're based on a wait time. And that wait time we found varied from a few days to, in one case we found up to a 14-day wait period, which again, no evidence for that, but just that's the common practice. In terms of the density targets range from a percent of maximum theoretical, which I'll volunteer as part of our spec. Maximum theoretical is not something you usually measure with recycled materials, so there's a thing we need to work on ourselves, to a percent of a control strip. So again, there's a lot of variability in there in what the target is, but also in addition, or how the target's measured, I guess, but then also in addition just to that percent, is it 92%, 95, 99%? There's a wide range there. One thing we really took out of the survey that I thought was very interesting, to me all of it was interesting, but anyway, more interesting I guess, when were the test results desired? So this is stuff that came back from both the contractors and the agencies. And if you look at the different shades of blue there, the dark blue, when do most people want data or information on when you can open the thing to traffic? The predominant test result was 1 to 4 hours. So again, focusing on our project, we know we need to be within that time range or curing range on the material, 1 to 4 hours. In terms of when to surface it, it was really within the first day. So again, a narrow kind of time range for us to look at in terms of the testing that we're going to do. In terms of other things we learned in the survey, the current practices for QC during or just after construction resolved primarily around density and moisture content. I don't think that's a surprise to anybody, but we documented that. Are these tests good indicators of future performance? Maybe. Moisture content, I think, is probably more debatable. I think density is probably a pretty good indicator of good performance, or excuse me, of poor performance. I'm not sure it's always a good indicator of good performance. The better your density is, not necessarily do you have better performance. But the worse density you have, I think you could probably say you probably have worse performance. But through that phase 1 survey, the literature, and talking to the folks through the kind of follow-ups to the survey, we identified 14 tests that we thought would make sense for us to consider for phase 2. So phase 1, part of the work was the survey, then also identifying the tests we wanted to follow up. So we found 14 tests that we started to fiddle around with. One of the biggest things that we found, I thought that was most useful, was a series of research reports sponsored by Utah DOT. And they looked at different methods to assess emulsion CIR. And some of that was mentioned during the committee meeting on Tuesday morning. In terms of tests that they're using a shear or vein stability test, vein shear test for stability measurement, a dynamic cone penetrometer test to look at penetration resistance, and then also a field Marshall hammer to look at deformation resistance. So taking the upper assembly of the laboratory Marshall compactor and then driving that into the pavement section. They also developed guidelines for emulsion-based CIR, so that's given us a place to start with some of these tests. And so we have taken a few of those and modified them a little bit for our work. This just shows an example from one of the reports. The thing there on the left is the vein shear device. So they drive that into the pavement, count the number of blows it takes to drive that into the pavement. That's one test. And then another test is they put a torque wrench on that and it measures the shear property of the material. And then you see there on the right, the field Marshall hammer. Again, it's just the upper part of the Marshall compactor device, and they take that into the pavement section. So for phase 2, again, we had a lot of help from the contractors and also from agencies on getting material to us. And from the projects we had, we came up actually with 18 different mixtures. For the most part, we followed the mix designs, but in some cases we had a lot of material. Dave had some work on the test section there at UC Davis, and he sent us 20 couple 5-gallon buckets of mix, and so we were able to play with that a little bit and make a couple products out of it. And so based on that, we came up with these 18 different mix designs. You may see some of your sections in there if you donated material to us. But you see how it was all distributed across cement, no cement, foam and emulsion, and then the recycling processes. So the tests that we came up with, we were using them to evaluate the initial stiffness gain of the material, which is a way to look at the stabilization reaction. We looked at a shear and raveling resistance, which we kind of equated to an opening to traffic measure, and then also a shear resistance and a moisture content, which we looked at in terms of a time to paving factor. All the materials we obtained came from US and Canada, and again, a huge thanks to the folks that contributed to this. This project wouldn't be possible without all that assistance. We purchased a slab compactor that we used in the lab, and we used that slab compactor to make these various test slabs. So it's a steel mold about 20 inches by about 16 inches wide. We compacted materials to 5 inches deep. And so with the weight of that slab, those things are about 105 or 108 pounds a piece. So we moved through a lot of material in the lab. Our 5-gallon buckets, we found that a pair of 5-gallon buckets would make a test slab. So out of a dozen 5-gallon buckets, we had 5 to 6 test slabs that we were able to fabricate. And then the figure there on the right, I commented this to one of the receptions either last night or the night before. It amazed me the variety of materials that we had. The good performance that we got from them. And so just looking at those three materials, you can see there's quite a bit of difference in the properties of those materials physically, not only looking at the color, but looking at the gradation and some of the other factors that we studied. So it was a lot of information for me. And, you know, I think some people have told me that they consider me an expert in this field, but what I love about these projects, I'm still learning constantly by doing these things. And that's one of the more exciting parts to me about the work. So here are a couple examples of some of the tests we did on the test slab. We tried to come up with a way to do as many tests as we could in the slab without having one test influence the results of another, and so that was something that took time. And this was really about a 12 or 14-month process for us to go through all these materials and make all these test slabs. So we were in the lab probably 3 days a week, mixing material with our working foaming lab setup, using the pug mill side to mix materials, or using the foaming process whenever we were putting foam in. So the picture there on the left is one that is Ilker using the upper part of the Marshall hammer assembly. You can see we just pulled that off the Marshall compactor, drove that thing, and every five blows, up to 20 blows, we counted the penetration depth in the material, and that was one of the tests we did. The fixture there on the right is the concept that Dave Jones and the folks in California came up with for their shear measurement. So the shear vane device that I showed from the Utah DOT report, when they did that, they did some preliminary work in the field before we did a lot of the lab work. And they found that really disturbed a big area within the pavement section. And so they came up with this thing that's got these 3-inch long spikes on it. So there's 4 spikes surrounding a central spike, and you drive that fixture into the pavement. So one test is the number of blows required to drive that into the pavement section, and then another, you can see the hex head milled into the top of that. We put a 3/4 inch socket on that, and then a torque wrench on it. We measure a torque property, shear property with it. So again, that disturbs much less material than the shear vane device we initially looked at. We also came up with another device to measure raveling properties. It looks just like that device, except those pins 4 pins on the outside are shorter. They're 3/4 inch in length rather than 3-inch length. We chose those lengths because we thought most recycled layers would be at least 3 inches thick, so that way we can isolate the test only to the recycled layer, not get influenced by what was underneath. The raveling fixture, again, the same thing, just with the shorter pins. The idea was looking at the particle size of the recycled material. We figured probably 3/4 inch would be in the neighborhood of most of the recycled layer materials, and that way we can get an idea of what it looks like to try to ravel those materials out there. There are a lot of different things we tried. We considered, do you put a vehicle on top of there and turn the wheel to measure the deformation, but tire pressures, vehicle weights, and all that. Adam Hand, he bought a vacuum cleaner at the hardware store and ran a vacuum cleaner with the agitating brush over top that tried to measure something. We tried all kinds of crazy things, and these worked a little better. So I'll show just a quick example of some of the test results. This is some of the results of the lab work that we did, and so this is the torque value from that fixture that I showed there on the last slide. The torque value applied to that, and over 4 different curing times. And these are all the different mixtures, and I've got them grouped by, you see the acronyms across the top. EC is an emulsion cement mixture, so that may be CIR, CCPR, FDR. Again, you notice I'm not discriminating between the mixture types. Some of the other work we found a lot of similarity between the 3 process types, and so I've been spending more time focusing on things like presence of cement, or the additive, foam or emulsion, rather than the process itself. So emulsion cement going across the top, emulsion no cement, and foam no cement. And so a couple things I want to point out is just for this particular test, and we did find this for the other test, predominantly if you look in this case, the mixtures that had cement had a higher torque value. We found that to be fairly consistent for the other test. If it was a penetration resistance test, we found a higher resistance to penetration when cement was included, even at the curing times here, 1, 3, 6, and 24 hours. Another thing to note, you see how the symbols really stack on top of each other for the condition with no cement over that first 24 hours. There's not a lot of additional strength gain or whatever to the material, or whatever the property is that we're measuring. I'll call it a strength gain. Not a lot of additional strength gain over the 24 hours for materials that do not have cement in them. But you notice for the ones with cement, especially if you go over there and look at mixture 10, you see there's a wide range in the property, almost a doubling of the torque value between 1 and 24 hours, and that's really the influence of the cement in that case. So the cement plays a big factor into it. I think some of the literature out there talks about cement, especially in a foaming application, as merely being a dispersing agent for the foam. But I think this result, and then some of the work we did in the last NCHRP project, the 951 study that the folks that talked from Indiana yesterday mentioned, the laboratory work that we did on that, the cement plays a huge role in stiffness properties of the material as well. And I think that's pretty well documented by this slide, but then also some of the other work that we've done. So findings for phase 2, the laboratory work we did, all the tests that we came up with, this idea of these different torque devices or dynamic cone penetrometer, all the tests are relatively low cost, they're relatively simple to operate, they're quick to conduct, and really also easy to analyze. And those were some real goals that we had going into the work. We don't want to come up with a $100,000 fixture that we expect every contractor to go out and buy. These raveling fixtures, we've got some diagrams for them. We've had them milled about $100 a piece to have them manufactured. I think the DCP is the most expensive thing. It's about a $1,100 piece of equipment, but I think a lot of people, especially agency-wise, already have those, or maybe in the geotech section they already have those. So we're really trying to shoot for these practical and realistic tests. All the tests that we tested, all the tests that we analyzed in the laboratory portion, they've responded to changes in mixture properties, which was, again, one of the goals we were trying to find. They responded to changes in curing time and then also presence of cement. We found that the presence of cement was the most significant mix factor that we put into the matrix. Whether foam or emulsion was not as significant as having cement or not having cement. The difference between FDR, CIR, CCPR, again, was not as significant as having cement or not having cement. So phase 3 activities, this is where we are now. Again, started this work kind of beginning of this fall. We want to identify limiting criteria for the phase 2 test. So again, the idea of the phase 2 test, can these phase 2 tests document the changes in materials over time? And now we need to come up with, quote unquote, the magic number to say this is the distinction between a poor performing and a good performing section. The good thing is we've gone out to, I think we've covered in 6 locations, 11 different material combinations. The good thing is we found good materials everywhere. The bad thing is for our study, we haven't been able to identify a poor performing material because we haven't seen it yet. So we're going to get, I think, a little creative maybe this winter and next spring and how to come up with that. And we've got some ideas of how to do it. One of the other things we're doing is we're determining field precisions on replicate test. That's one of the things we have to come up with as far as the draft AASHTO standards that we're going to put together. So using a replicate piece of equipment and multiple operators, we've done that work. We looked into some work. With Ben being down at Auburn now, he was linked into some work that NCAT and Minroad were doing on a section in Minnesota about a month and a half or 2 months ago now. And so we were able to go there and through that course of testing on test sections they did just off the Minroad facility, we covered emulsion and foam CIR, emulsion and foam CCPR, and emulsion and foam FDR, all in one place over about 4 days. And so it was a great opportunity for us not to go to six different places to see 6 different materials. So it was really important for us to be there, and thankful to those folks for letting us come. So in terms of the tests that we consider for the phase 3 work, the work that we're doing right now, we're using lightweight deflectometer to look at stiffness properties of the material. This test has worked really well. The only downfall to the LWD is that it's got a zone of influence that's usually deeper than the recycled material itself. So we're getting influence on what's underneath the pavement section, the recycled section as well. Dynamic cone penetrometer, again, standard test. This shear device that I showed in the slide a couple slides ago, we're doing a torque value on that, and then also a number of blows to drive that into the pavement section, wondering whether or not maybe we can get rid of the DCP test if we count the number of blows for the shear device. So again, we're thinking about ways to simplify the work we're doing. And then the raveling test, where again, we're looking at a torque value for that raveling fixture that has the short pins, and then also the number of blows to drive that thing into the pavement section. So every time we go out to the field, we're running these tests. We set up what we call a test block. We've got these tests randomly distributed over a test block that's maybe 6 feet long by about 3 feet wide, and we do replicates of each of those tests, so 3 replicates within each of these test blocks, and then we try to do replicate test blocks within the same curing time or over different curing times. So some of the data that I'll show are the averages over these test blocks or over the triplicate measurements. So in terms of the work, again, we've done so far, this is the matrix we've covered. We've been to New York, Minnesota, South Carolina, Indiana, on this side of the country, well, not this side, my side of the country. Now I'm over on the other side. And then project in California and project in New Mexico, and we'll have, I think, 2 more California projects coming up. So with that said, for this matrix that I show right here, technically we've met the objectives of the study as we proposed it, I guess almost 3 years ago now. But I think the project panel wants to do a few more. We'll have some funding, I think, left over next year. So in terms of that, we will be looking for additional projects next year, early in the construction season. So if you're somebody, an agency or contractor that knows a project's coming up, again, we're looking for asphalt stabilized, CIR, FDR, and CCPR. If you have a project someplace that you'd be interested in having us come out and just kind of hang out with next to the rollers, we would really appreciate knowing about the projects and try to fit those in. Again, I'm looking for probably another maybe 6 or 8 projects or something next spring. And so if we could fit that in, that would be a huge help to us. The only thing we do is we stand near where the rollers are, and then once the roller's finished and all the density testing is done, we go in and we do our little test, and then we're out. And so it's really the idea is to stay out of the production. We're trying not to influence any of that. You see the little star next to the state, Minnesota. That's our interlab study site. One of the things we were trying to do with the laboratory testing was to make slabs, send those around, and then have everybody do the same test on them. But if you think about sending a 100-pound slab, one, how can you send it reasonably? How can you send it without damaging it? And how do you send it at early ages and count for shipping time from Virginia to California or Virginia to Nevada? Just no way to do it. So what we proposed to the panel was to do we call it an interlab field study. And so the interlab field study we did in Minnesota, and I'll show a few more photos of that. So this is what our test block looks like. That's Dave and his student there on the left, and then student Stefan on the right. You see the little dots, those are our test locations for each of the tests. So those show our triplicate measurements for all the different tests we covered. The kind of line in the middle is where we have folks from the agency do the nuclear density testing, so we're trying to include that data in there as well. Dave and Stefan, you can see in the figure there on the right, they've used the upper part of the DCP to drive in their shear fixture. They've driven that into the pavement, and then there on the right, Stefan's got a torque wrench on it. He's applying the torque measurement to it. So again, one test, 2 measurements we're getting out of it that are related but not well correlated, so we're measuring different properties. And again, this whole process, we got it down to about 25, 35 minutes to do all the tests in that little test area. Ilker and Johnny there from my office there on the left, kind of doing the same thing at Minnesota. And then you see here is a little different way we did the torque measurement. We actually used a couple barbell weights for this test setup we had. Again, looking for simple and not costly ways to conduct the testing, but ways that are repeatable. So 2 barbell weights, 2 10-pound weights we put on top of the fixture to apply a normal force to it so the fixture doesn't lift up when we're applying the torque to it. And then he's applying the load to it. We record the torque value from it. This is what the pavement section looks like. That's our test fixture. Again, you see it's driven into the pavement. The torque's been applied to it. You see the little cracking coming off it. That's the result from the shear test. And when we pull that up, you can see our disturbed area. So that fixture is about a 5-inch diameter circular plate on the top. And so that's our distressed area. And what we found is even at the at the 24-hour time period, the little ridges and humps and whatnot, you can take your shoe and kind of push all that stuff back together. And once we're gone, you really can't tell what we did except for maybe a little sand that we left over when we do the geogauge stiffness test. So these sections at Minnesota were open to traffic really right after we did the work on it. They did not fog seal it before traffic was put on it. We had no issues the next day when we came back and looked at these sections where we did the testing. So we're not destroying the pavement by going out and testing. I know some folks have been a fear to that, but that's one of the things we're trying to consider too, is not doing that. And then this is the entire group. The folks from Nevada on the right, Virginia in the center, and California there on the left. This is us doing all of our sections for this. So this is the interlab field study. And so we all took the same sections at the same time, ran the different tests, and then we've gone through and quantified those tests. That's how we're coming up with the bias of repeatability statements for the specifications. And so again, a lot of cooperation went into this whole process, and a lot of help from other folks. And so I really appreciate all that. Just a couple examples of some of the data. One of the first things we looked at was to see whether or not in the field testing, did our field testing confirm or kind of repeat the findings that we saw in the lab testing. And that was one of the biggest things that we did find, is that we noticed the same trends and the same, response to the material properties in the lab, or excuse me, in the field as we found in the lab. So I know there's a lot going on here. One thing I'll try to focus on is maybe that from the center part of the figure over to the right, you see there's a CIR emulsion section. And you look at the different curing times of 1, 3, 6, 24, and even 48 hours. You see in general the torque value from the shear and the rattling test increases with time. In terms of the numbers across the bottom, those are the individual test blocks that we included. So again, I showed that layout where we did the triplicate test of 5 or 6 tests in a 6x3 area. That's one test block. So if you look at, for instance, the 1 hour test on the CIR emulsion, we've completed 9 test blocks using that so far. And then the error bars on the top are the plus or minus 1 standard deviation. So what surprised me, I guess, in some ways in this data is how tight our standard deviation was. So we've done a good job of coming up with tests that are repeatable and can be performed, I think, by most folks in a reasonable way. If you also look on the left side of the figure, the CCPR foam and cement, the CIR foam and cement generally have a higher torque value than the corresponding material without cement. So again, following the similar trends we found in the laboratory. So these were all pretty promising. One thing we did find, and I won't explain how we came up with it, but on the FDR emulsion cement there on the far right, we found a low density section and a quote unquote normal density section. And so we decided to test those. We verified that with a nuclear density gauge. It was about maybe 10 pounds difference in terms of the density. And then we ran our test on it, and lo and behold, our test showed that test result as well. So again, based on this, we're showing changes with respect to material properties, but we still don't have that magic number to say what's good or what's bad. And so that's another part we'll be concentrating on coming up. If you take that same information, maybe make it a little easier, start to look at, here's a 1 hour curing time. And the way we defined curing time was based on the time after the compaction was completed. So once the rollers were off, the density testing was worked. For the most part, we were able to go on there within an hour after the final roller. And what was, again, interesting, finding the same things, the materials that included cement versus not cement, the ones with cement had the higher torque value, even just at 1 hour. So again, a little more work to be done here, but this is just some of the initial information that we found. We had some discussion at the Cold Recycling Committee meeting Tuesday morning about dynamic cone penetrometer, so I'm glad I had included the slide already. So one of the things we did was included, again, DCP, and one way you evaluate the test is look at the millimeters per blow on the test, or a DPI value, a dynamic cone penetrometer index value. And you can see, again, following the same trends. In this case, since it's a penetration resistance, the lower the value is, the quote-unquote stronger the material is. So if you look at the materials that have cement, in general, the penetration or the number of millimeters per blow is less than those mixtures without the cement included. Again, if you look over to the far right, you see the low density FDR section, and it followed really the trend we were expecting to see. So remaining project task, field testing, I said 4 or 5 more projects by, let's say, mid-2020. That's assuming that the project panel gives us an extension, which they had hinted at last summer. Right now, the project is supposed to wrap up officially May or June of 2020. If they give us an extension, it will probably wrap up by the end of 2020, and hopefully we'll have a final report out, I'd say, by early 2021. So it's still a little bit of time, but hopefully some of these updates we can start getting the information out a little ahead of time. So not only are we doing the field testing, we're also working on specifications for each of these tests. We'll submit draft AASHTO specifications for the folks to be able to use, and guidance on how to use the test, and guidance on how to apply the specifications. We'll be developing implementation products. So there'll be some sort of training mechanism for all these different tests for us to go out, or someone to go out and talk to the agencies and the contractors about how to run these tests. And again, a final report, probably late 2020 to the panel, probably early 2021 out to the public. That's everything I got. I'd be happy to address any questions if you have them. Thank you very much.
All right. Just have a few remarks before we send you on your way. So I hope everybody, thanks for staying, by the way, first off. And thank you for spending the last several days with us. AIR represents responsible, renewable, I'm going to get this right one time. Responsible, renewal, reliable results. And we hope you've learned about tools that will help your business and improve your bottom lines, either for your company or for your taxpayers, depending on which side you're on. We hope you've made some valuable connections with others in the industry. Networking is very important at this meeting. Also, I hope you've enjoyed your time in Monterey. I think if you didn't, I don't know what you were thinking. And please take a moment to let us know that what you've thought of this year's meeting. There is a survey through the app that you can submit. We really want to hear your feedback. If there were things that we could improve on, please let us know. I think a key thing, it's easy for us to go back to our sort of day-to-day and forget about ERA somewhat. Please, one thing that Don Johnson, who used to be very involved in this association, kind of guided me on was he would block off just an hour a week sort of deal to focus on ERA and do some work for ERA. So try to do that. It might not get it in every week, but turn your eyes back towards ERA and keep this momentum going. Speaking of momentum, the annual meeting will be in San Antonio, February 17th through the 21st. Our semi-annual meeting, this again, will be in Charleston, South Carolina, October 26th through the 29th. Oh, well, look at that. Good timing. You're the man. Again, I'd like to thank Federal Highway Administration and Caltrans for their support of this. It was great turnout due to that. Our sponsors, I think I won't go through the whole list as a matter of time. Our ERA board and the committee chairs, and last but certainly not least, our program committee, who really did a lot of the legwork on this. Ryan Essex, Dennis McElroy, Trevor Moore, Steve Cross, Rick Church, and Ali Mastardo. Thank you for coming and look forward to seeing you soon.